Hello, everyone. My research topic is characterizing thermo-hydro-mechanical behavior of inclined heterolytic sequences. And as we know, Canadian has the third largest proven oil reserves in the world, and the majority of them are found in Alberta's oil sand. The McMurray Formation is the major pay zone of oil sand, consists of a wide range of lithophyses, including bitumen-saturated oil sand and interbedded sandstone and shale in the form of inclined heterolytic strata, so-called IHS. The efficiency of in situ recovery is significantly affected by the presence of IHS, as it might hinder the propagation of the steam chamber during the SAGD operation. The injection of high pressure and temperature steam into the Athabasca reservoir may lead to shear failures that create preferred flow passes in the reservoir. The lack of existing study on IHS is limited due to its great heterogeneity and complexity. As a result, the limited experimental studies are preferred to simulate its behavior during the SAGD operation in terms of thermo-hydro-geomechanical properties. The major goal of this study are examining the rule on the geomechanical constitutive behavior of IHS, the artificial sand, mud, and IHS samples will be investigated under the similar heating and loading environment as the SAGD operations through a series of laboratory tests. And here you can see the full chart of the experimental analysis of this research. As we know, in general, there are two predominant stress passes are followed within the reservoir during the SAGD process. And for example, this is the failure envelope of this oil sand, and this is in PQ space. Assuming total stress does not change, the induced in steam will cause the pore pressure to increase. And therefore, the sigma prime 1 and sigma prime 3 will increase at the same time. And therefore, there will be no deviator stress change. But increase in sigma 1 and sigma 3 prime will cause the mean stress to increase. And assuming here is the initial state, the first flow path will look like this. And secondly, the horizontal total stress will increase due to thermal expansion of the reservoir within the steam chamber. And assuming no pore pressure changes, these effects result in the development of shear stresses and the stress passes where the shear stress and the mean effective stress will increase together. And the second flow path will follow this way until it reaches the failure. So as the result, the designed SAGD stress path in this research will consist of two components. The first is reducing the confining stress from 1 MPa to 0.1 MPa. And secondly, the triaxial shearing under effective confining stress from 0.5 MPa to 4 MPa. The test specimen is artificial with the following variation: the degree of bioturbation, inclination of shale bedding, and also the thickness. And the temperature change from 25 degrees Celsius to 200 degrees Celsius will be also considered. And here is the major component of the experimental analysis. The isotropic cyclic consolidation test followed by a drained track cell compression test. And the permeability will be measured during the drained track cell compression test. Then, in addition to the experimental investigation, the numerical simulation on IHS will be established using Black 3D. The geomechanical behavior of IHS under a range of temperature and loading passes can be modeled using a strain softening Moore Coulomb model and matching the experimental results. And furthermore, machine learning technique will be used to generate proxy models for IHS with different configuration of shell beddings for stress-strain relationships, filler mode, and permeability changes for IHS. And by using this technique, a full field coupled reservoir geomechanical simulation can be performed for large oil sand reservoir that helps to optimize recovery efficiency and perform the risk assessments during in situ recovery and open pit mining. And here comes the actual experimental analysis. At the isotropic cyclic consolidation test stage, a carbon fiber enhanced isotropic cell is constructed to correlate pore pressure with different confining stresses and also the change in permeability. And this cell aimed to conduct CT scans analysis on artificial oil sands during isotropic cyclic consolidation test. And in order to do so, this cell has to satisfy two requirements: the X-ray transparency and ability to hold at least 3 MPa internal fluid pressure at appropriate factor of safety. And here is the test results for the carbon fiber enhanced isotropic cell. The carbon fiber rod is the weakest point of the cell, and it is designed to carry at least 27.7 kilonewton of tensile load to achieve 10 MPa of the cell pressure capacity. And from the rod tensile test results, all rods are filled at the epoxy connections with the minimum tensile strength of 20.9 kilonewton and the maximum of 32.4 kilonewton. And the pressure test of the entire isotropic cell is also conducted. The cell filled at 5.13 MPa due to 6 out of 8 steel insert share of the tie rods. And this number gives a factor of safety of 1.7, which is good enough for this experimental investigation. A rigid dummy sample is used to test the X-ray transparency. And here is the quick shots of the results. It shows a very good penetration X-ray through the carbon fiber enhanced wall. And the cell was filled with Canadian oil. It also shows very good X-ray transparency with the Canadian oil. And here presents the CD scan results for the frozen artificial Tilling sand sample and the artificial oil sand sample at 0 confining pressure. From the porosity results, the porosity for Tilling sand sample is 29.9%, and for the artificial oil sand sample is 18.7%. The porosity is calculated based on the pore space, including air, water, and bitumen. This means Tilling sand sample is not representative for locked sand structure due to the enlarged pores from frozen water at 0 confining pressure. The enlarged pores also reduce tortuosity, and we can see here a very large percentage of pores having a tortuosity of 1. And on the other hand, the oil sand sample presents a better structure due to better compaction during sample preparation. And we can see very good scattered tortuosity throughout the pores. So in the future, the CT scan will be conducted on both types of sample at 250 kPa, 1 MPa, and 3 MPa confining pressures, and as well as on an in situ oil sand core at those pressures. And hence, a complete correlation of pore structure change with confining pressures will be fully developed. The calibration will be also developed for the future modeling purpose. And thank you very much.